So this brings us to a theorem that we get for this section. For our differential equation, if we let, and this is obviously, specific to complex eigenpairs, but let our y of t equal u of t plus I times v of t. Okay, this is going to be our solution where u and v are real vector valued functions, real, because we've pulled out the imaginary components. Okay, v represents all those imaginary parts of y. Okay, now, so from our example, what that means is that u, what we found, is equal to e to the t cosine t. That was the one that was attached to the real parts. Negative e to the t sine t was the second element there. And then v, because it was all of the imaginary parts, would look like e to the t sine t, e to the t cosine t. Okay, so that means that y is equal to c sub 1 times what we got for u plus c sub 2 times what we got for v. Okay, so this is what our solution will look like when it comes to these complex eigenpairs, okay? So what we're going to do, we'll kind of do a guided example here together. And for this guided example, pause when you need to and, start back up when you're ready. But we want to make sure that, we kind of have another good worked out solution for you here. So I want you to try this one right here. So go ahead, pause if you need to, find the determinant, and let's figure out what those eigenpairs are. Okay. So if you paused and you found what we should be getting is, let me just do something real quick here so this doesn't move around on me. Okay. All right. So the determinant of A minus R lambda identity, which A minus lambda identity would look like this. And we would get, multiply that out, -6 lambda plus 13. I'm sorry, lambda squared there equals 0. All right. So lambda equals 6 plus or minus the square root of 36 minus 52 all over 2. All right, so what we should be getting here for our lambda pairs, our eigenvalues, is 3 plus or minus 2i. Okay, so we are going to go ahead and just work this out for lambda sub 1, and that would be our 3 plus 2i, and remembering that we're just going to get a conjugate pair for the other. All right. So if I take 6 minus the quantity 3 plus 2i, I get 3 minus 2i here. If I just take the negative of lambda, I get -3 minus 2i. So my matrix should look like this, solving for x1, x2. Well, let me do a matrix with 0 elements. There we go. All right, so this step, it's really up to you which one of these rows you want to use to do some solving here. I'm going to go with row 2 just because it doesn't have a 13 in it. So it looks like we would get x sub 1, and then I have -3 minus 2i times x sub 2 here. So I'm just going to go ahead and do that. Is equal to 0. Now, what I typically will just try and do here is I'm just trying to make things easy on myself. So a lot of times, like you kind of saw in the last one, if I have -3 minus 2i, my complex value that's being multiplied by x2, a lot of times I'll just make x2 equal to 1. Because if I do that, I just make that 1, then that means that in order to solve for x1, I just move everything to the other side. So it looks like x would be 3 plus 2i, just to kind of make it easy peasy for myself. So that eigenvector would look like this. Okay. And so we're going to go ahead and this is where it gets tricky, and this is why we're going to kind of do this as a guided example together. We're going to go ahead and put this into our general solution, y of t. Now, while I am going to include the conjugate pair, we are really just going to continue to work through this with our first solution here for lambda. And even though I'm putting this into this form now, we will obviously be changing this out of here and using Euler's formula. Okay. So it would look a little something like this. And this is where I'm going to just kind of ignore this second piece, and I'm just going to work with this first piece. Okay. So we should get c sub 1 e to the 3t times the quantity cosine of 2t plus I sine of 2t. And that is just using Euler's formula there, where you know, this is A and this is B. Okay, so just using Euler's there. And then bringing back my eigenvector. Okay, now kind of like I did above, I am going to go ahead and I'm just going to do my distribution here. Just to make this next step a little easier on myself. Because I'm going to have to distribute here as well. Okay, so this does get kind of nasty. So you show as many steps as you want with this. I'm going to go ahead and distribute everything to that 3 plus 2i. This is going to get a little sticky, but we are going to get 3 e to the 3t cosine 2t, and then multiplying by the 2i. So plus 2i e to the 3t cosine 2t. And now distributing here as well. So plus 3i e to the 3t sine of 2t. And then distributing. So here I'm going to get 2i times I. So it looks like I get minus 2 e to the 3t sine 2t. Phew, okay, there we go. When I multiply that by 1, it is not so bad. So we're going to go ahead and just e to the 3t cosine 2t plus I e to the 3t sine 2t. Okay. Checking to see if I forgot anything here with those notes. I think we got it. Okay. Fingers crossed. All right, so we are going to separate out our real and imaginary parts here. And remember that those imaginary pieces get lumped in with our C sub 2. Okay, so we're going to keep the real parts with C sub 1. So my real pieces being boom and boom right here. All right, and then from element 2 down here, just e to the 3t cosine 2t. All right, so then we are going to have I times C sub 2. We can go ahead and call it that. I know we used C sub 2 up here, but again, remember the only difference will just be a scalar multiple of -1. So we are covered, wrapping that up into a constant. All right, so for my imaginary pieces, boom, boom, and from here, there. Okay, so we are going to go ahead and pull the I from each of those, leaving 2 e to the 3t cosine 2t plus 3 e to the 3t sine of 2t, and then e to the 3t sine 2t. Okay, now typically what we also like to do with, these answers is go ahead and pull out, we have that common factor of e to the 3t that we can also bring out of this. And then, we are going to go ahead, I'm just double checking everything here. Okay. So, we are going to go ahead, like I said, let's bring out e to the 3t, which would leave us with 3 cosine 2t minus 2 sine 2t, and then cosine 2t here. And then we can say that this is just going to be our C sub 2. I know I pulled the I out there, but it is wrapped up in the C sub 2. So 2 cosine 2t plus 3 sine 2t. And then sine of 2t here. Okay, so this is what, let me pause for just a second. Okay, sorry, I had to pause real quick. I know you didn't probably notice anything. I just wanted to make sure, and if you've hung in with me this far, great job. Congratulations, you're awesome. Because this is obviously a long problem. There's a couple different ways. Now you could totally, this is what I wanted to make sure of. You can represent your answer for y of t just like how we left it right here. So this is a perfectly fine representation here for your general solution, okay? What you may also be asked to do for some of these is identify from theorem 4.7 what is u and what is v. Okay, we basically did that right here. This was our u vector according to that theorem, and this was our v vector. So basically these last two steps that we showed here, you just have to kind of take a look, and it'll mostly ask you to separate out the real from the imaginary and maybe give a general solution like we did here in the last step, or separate real and imaginary and then just, discuss what the u vector and the v vector look like. So let me know, we will kind of pick up with this again on Tuesday as well, just to keep practicing with this idea. Let me know if you have any questions.